Welcome to this video where I take a look at some miscellaneous aspects of the theory of Whitehead and Russell's Principia Mathematica. This video is in many ways separate from the series of videos that I've already started to make on Principia Mathematica in that it doesn't just continue on from where the previous video left off. Yet in this video I'll be aiming to go into the details of some things that didn't really find a place in the original series of videos. So I better say this now before I'm accused of wasting anyone's time. This video is for those who are a bit more hardcore about Principia Mathematica. It will require some existing knowledge and understanding of Principia Mathematica for you to understand some of the things that I'm going to be touching on in this video. Some of what I've covered in my previous videos will be assumed in this video. If I don't explain something in detail here, then it may be that I've already explained it in another video of mine. So I was originally hoping to just have a single video on Principia Mathematica Miscellanea, but there's probably going to be a second video as well. I'm also considering a video which doesn't really focus on the theory of Principia Mathematica, but in which I give a bit of a personal account as to why I seem to be so fixated on Principia Mathematica, why I find it so interesting, and how I've gone about trying to understand some of its contents. This latter video would really just be me talking about some of my personal experiences and ways that I've resolved certain issues with Principia Mathematica. This video though is really going to be exploring the limits of my understanding of Principia Mathematica in certain respects. Whitehead and Russell don't always explain things as clearly as they could be explained, or at least in some cases what they write doesn't necessarily give clear insight into how they viewed things. There's a certain amount of subjectivity involved in the interpretation and understanding of Principia Mathematica. Russell was deeply involved with philosophy, and in later years Whitehead turned towards more philosophical pursuits. The explanations of some concepts and ideas rely on adopting a certain somewhat subjective philosophical point of view, which may be far from universally accepted. For someone with a background in mathematics, this can be a bit of a shock and sometimes quite frustrating. Sometimes we can be trying to look for the way of interpreting or understanding something in Principia Mathematica, when really there are several possible ways of understanding, and we may personally come to a different interpretation or understanding of things than did the authors, especially when the authors didn't specify exactly how they intended things to be understood, or maybe they weren't even sure themselves. In Bertrand Russell's autobiography, we read in one of his letters, dated 13th of September 1923, to Jean Nicot, Principia Mathematica is being reprinted, and I am writing a new introduction abolishing the axiom of reducibility, and assuming that functions of props are always truth functions, and functions of functions only occur through values of the functions, and are always extensional. I don't know if any of these assumptions are true, but it seems worthwhile to work out their consequences. Some of the interpretations that I've provided in previous videos in this series are partly my own interpretations. This video will be no exception. My interpretations are based on what Whitehead and Russell have written, but I've had to step in and fill in the gaps from time to time. Therefore, some of what I say in this video is provisional, subject to revision, and, dare I say it, may be incorrect. I'll try to justify as much as possible what I say. It's clear that Principia Mathematica is a very complicated system. The 3 volumes of Principia Mathematica run to nearly 2,000 pages, and yet even those nearly 2,000 pages are only looking at certain parts of the whole system. The authors had a certain goal in mind, and they have, quite reasonably, limited what they discuss and the parts of the system of Principia Mathematica which they describe to those things which are pertinent to achieving their goal. Nevertheless, there are other parts of the system of Principia Mathematica which don't really receive anything more than a couple of short paragraphs here and there, and these parts may not be, strictly speaking, necessary for the authors to achieve their goal. However, some of these other parts to Principia Mathematica are sometimes worth spending some time thinking about in some detail, because by considering these other parts of the system in more detail, you're often forced to contrast them with the parts that are considered useful. And in this way, you may come to a better understanding as to why the useful parts are considered useful, but also you may realise that there are certain details about the useful parts that only become clear when placed side by side with these other parts and some comparisons made. Overall, you can get a much more detailed picture of the system of Principia Mathematica. So let's get started with the so-called propositional hierarchy. In Principia Mathematica, Whitehead and Russell sometimes make brief references to the propositional hierarchy. The references are often just passing references, and there's very little information explicitly given as to what the propositional hierarchy looks like. However, we're told on page 58 of the introduction that the propositional hierarchy can be derived from the functional hierarchy. So in this video, I will explore this idea in more detail, where I'll use what little information that we find amongst the pages of Principia Mathematica, along with my understanding of the system of Principia Mathematica, to have a look at what this derivation might look like. There's a lot that I want to say about this, and as I've said in a previous video, I'll take as long as I need in order to say what I want to say. My explanation of the propositional hierarchy is in large part an interpolation of the scraps of information that were given in Principia Mathematica about the propositional hierarchy. What I present is speculative in many ways and may not accurately reflect what Whitehead and Russell ultimately had in mind. The partial derivation of the propositional hierarchy which I present in this video is based on the contents of the first edition of Principia Mathematica. I have briefly read the introduction to the second edition, but I've not read it in detail and I'm not completely familiar with the contents of the second edition. I am aware that there are some significant differences between the first and second editions. However, there may be certain passages, particularly from the introduction to the second edition, that I may refer to. If I do refer to the second edition, then I will make this clear. The propositional hierarchy is not necessary to understand Principia Mathematica. I'm not aiming to provide a comprehensive treatment of any aspects of Principia Mathematica in this video. This video is simply me having a play around with some of the ideas and seeing what happens. That's what I like to do. As I've already mentioned, this is a partial derivation of the propositional hierarchy. When I set about doing this, I had no idea how much work was going to be involved. Suffice it to say that it's been very time consuming to get to the point that I've reached in this video. Maybe I'll pick back up at a later date and finish what I started, or maybe not. There are many things that I haven't managed to completely figure out, and some things that I haven't even got round to thinking about. Many of the ideas that will be expressed in this video have come to me as I've actually been making the video, and so I've not necessarily had the time to think through some of the ideas completely. In fact, one of the reasons that I make these videos is to stimulate ideas. Making videos such as this one seems to force me to consider things in more detail than I otherwise would, and therefore some things are without a definite answer at the time of making this video. The propositional hierarchy comes into play when we want to start introducing apparent variables which involve propositions, rather than apparent variables which involve individuals or functions. This is very rarely done in Principia Mathematica and is never done in a way which is relevant to the development of the system. Indeed, on page 134, in the summary of chapter 9, we read, "Since we never have occasion in practice to consider propositions as apparent variables, it follows that the hierarchy of propositions, as opposed to the hierarchy of functions, will never be relevant in practice after the present number." So where in Principia Mathematica is the propositional hierarchy used, or at least mentioned? On page 44, the authors explain the need for different types of propositions, and we see that propositions appear as apparent variables. On pages 57 to 58, the authors give a very brief description of the propositional hierarchy, and it's this paragraph in particular on which most of this video is aimed at explaining in more detail. Page 134, the authors give another brief explanation of systematic ambiguity through the use of propositions as apparent variables. On pages 193 to 194, propositions appear as apparent variables in the demonstration of proposition 14.3. So you can see that there are surprisingly few references to the propositional hierarchy. Hopefully you may appreciate then potentially how difficult it's been for me to try to figure out some of the details in this video. I'll not be going into any more detail about the functional hierarchy than I need to in this video. I've already made a video about the functional hierarchy in the video which covers the contents of chapter 12 on the axiom of reducibility. and I'll be assuming that the contents of that video have been sufficiently well understood. Therefore, if you don't know about the functional hierarchy, then some of this video will probably not make sense. Even so, there are some concepts from the functional hierarchy that it would be well to just remind ourselves of. The term predicative function is a primitive concept and thus is not defined within the system of Principia Mathematica, but can be explained in an informal sense. And examples of predicative functions can be exhibited. The concept of predicative function is important to understand though, and so I'll just spend some time clarifying what is meant by the term predicative function. Now, unfortunately, in Principia Mathematica we're presented with two slightly different versions of predicative function. There's the prototype version, which is given in the introduction, and then there's the final version, which is given in chapter 12. And I can't remember how clearly I distinguished these two versions in the video that I made covering chapter 12, so I'll just clarify here what the two versions are and which version I will be using in this video. In chapter 12, the notion of predicative function is identified with the notion of matrix, which, if you read chapter 12 before reading the relevant parts of the introduction, you might be left wondering why the authors have two terms for one and the same concept. But this identification is not made in the introduction. The terms predicative function and matrix do not necessarily have to be identified. The functional hierarchy is described in both the introduction to Principia Mathematica and in chapter 12, and confusingly, the descriptions differ in many respects, and this has caused me endless problems in the past, but I think I've managed to figure out what's what. So in the introduction on page 56 we read, if a function has several arguments and the highest order of function occurring among the arguments is the nth, we call the function predicative if it is of the n plus 1th order, i.e. again, if it is of the lowest order compatible with its having the arguments it has. I would also add that we can have individuals as arguments. Individuals are not functions, but can be arguments of functions. In chapter 12 on page 172 we read, a function is said to be predicative when it is a matrix. And it's also worth noting, while we're on page 172, matrix or predicative function is a primitive idea. So what's the difference? Well, what's called a predicative function in the introduction is a much more general kind of function than what it is in chapter 12. Functions can have different written forms. For example, a function of a single individual variable may be written as, say, psi x, but this function may contain apparent variables which are not explicitly mentioned when we represent the function as psi x. Indeed, we may find that we can write the function in the form for all y, phi xy. So we can think of there being a kind of unabbreviated form in which a function can be expressed and which clearly shows the apparent variables which may be involved. If we write the function in this unabbreviated form and find that there are no apparent variables, then the function is a matrix. Again, matrix is a primitive idea. Thus the following are matrices: phi xy, phi xyz, f of phi exclamation mark blank, psi exclamation mark blank, and so on. But the functions shown on the screen now are not matrices, since they contain apparent variables. Thus, in chapter 12, predicative functions have the form of matrices. Moreover, in chapter 12, the variables of any function will typically range over matrices or individuals, and this restriction on the ranges of variables is made possible by the axiom of reducibility. Note on page 172 we read, the variables occurring in the present work from this point onwards will be either individuals or matrices of some order. However, the functions for all x, phi xy, for all x there exists y, phi xyz, and so on, though they may not be matrices, if they are of the lowest order compatible with their arguments, they're predicative functions in the sense mentioned on page 56. Note that matrices in both cases are predicative functions, since they, matrices, are always of the lowest order compatible with their arguments. So the predicative functions of chapter 12 are much more restricted than the kinds of predicative functions of the introduction. And notice that on page 57 of the introduction, the axiom of reducibility has not yet been introduced, and so the further restriction of predicative functions to matrices is not as justified there as it is in chapter 12. Now, because my explanation of the propositional hierarchy is motivated by the comments on page 57 and 58, I'll be taking the more general notion of predicative function, which allows for functions other than matrices to be called predicative. Moreover, the variables of functions in the introduction are not limited to matrices. Despite matrices seemingly being pushed into the background, this is not the case. In fact, it will be well also to explain why matrices are important. Indeed, later in the video, I'll be making extensive use of the concept of matrix. So on page 169, we see that any possible function other than a matrix is derived from a matrix by means of generalization. Thus, matrices are the source of all functions in the functional hierarchy. But matrices are also the source of all propositions. Every proposition is derived from a matrix by generalizing all of its variables, or by substituting constant values in place of the variables. On page 170, we see all propositions with the exception of such as are values of matrices are also derived from matrices by the process of generalization. Elementary propositions are the values of matrices when all of the variables are substituted with fixed values, and I'll be saying much more about elementary propositions in a few minutes. A first-order proposition is derived from a first-order matrix by generalizing all of its variables. A second-order proposition is derived from a second-order matrix by generalizing all of its variables, and so on. On page 58, we see we may define a proposition of the nth order as one which involves an apparent variable of n-1th order in the functional hierarchy. Note that the term matrix relates to a concept within the functional hierarchy. Whitehead and Russell do not explicitly describe an analogous concept of matrix, if there is even such an analogous concept, within the propositional hierarchy. So for the time being, whenever I speak of a matrix, I'm necessarily referring to a function from the functional hierarchy. So what do we expect the propositional hierarchy to look like? Well, in many ways, I suppose we expect it to be similar to the functional hierarchy in certain respects. We start with elementary propositions, the most basic kind of proposition. We can form functions of elementary propositions. We can generalize over the variable or variables of these functions to obtain higher order propositions. We can form functions of these new higher order propositions. We can generalize over the variables of these new higher order functions to obtain even higher order propositions, and so on. But as we will see, this is maybe a bit too simplistic, but it's a start. Since we're looking to derive the propositional hierarchy from the functional hierarchy, then we need to figure out which parts of the functional hierarchy corresponds to the various parts of the propositional hierarchy. Some of the connections between the propositional hierarchy and the functional hierarchy are not too difficult to make, but others are more of a challenge. For this reason, I only give an incomplete description of the derivation and structure of the propositional hierarchy in this video. My first job is to try and clarify some of the claims on page 57 that elementary and first order propositions are of one or other of the three forms shown, where phi exclamation mark x is a predicative function of an individual. So let's start by having a look at elementary propositions. These are the most basic type of proposition. Let's figure out which parts of the functional hierarchy corresponds to these elementary propositions. Elementary propositions are the values of matrices, and remember, matrix is a functional hierarchy concept, after replacing all of the variables with suitable fixed values, so it may seem that we can just stop there, and in a sense we can. However, for reasons which I'll explain as the video progresses, when dealing with the propositional hierarchy, we only need to consider the values of a relatively small number of matrices. So let's have a look at what Whitehead and Russell have to say about elementary propositions. On page 57 they say, propositions which contain no functions and no apparent variables may be called elementary propositions. On page 95, we see the notion of elementary proposition introduced as a primitive idea. By an elementary proposition, we mean one which does not involve any variables. On page 132 we have a proposition which contains no apparent variables is called elementary, and a function all whose values are elementary propositions is called an elementary function. And on page 168 we see propositions which contain no apparent variables we call elementary propositions. And finally, from the second edition of Principia Mathematica, on page 22 of the introduction, a matrix is a function of any number of variables, which may or may not be individuals, which has elementary propositions as its values. So what's to follow is how I currently understand certain aspects of Principia Mathematica relating to elementary propositions. The values of matrices of any order are elementary propositions. However, I make the initial claim that all elementary propositions are the values of first order matrices. So let's take a look. We have first order matrices of a single individual variable. I don't necessarily want to give the impression that there are finitely many or even denumerably many first order matrices, but just for illustrative purposes, suppose we have phi1x, phi2x and phi3x, which have the values as shown. And suppose we also have first order matrices of two variables such as psi1xy, which has values as shown, and similarly for functions phi2xy, chi1 xyz, and so on. All of these values are elementary propositions. That is, they're propositions which have no apparent variables. We can think of the values of each function as corresponding to a certain class or collection of propositions. Whether the propositions hold or not is unimportant here, simply that each of the propositions is a value of that particular function. Now let's consider the second order matrix f of phi exclamation mark blank, which has values of the form phi exclamation mark a, where the variable phi exclamation mark blank ranges over first order matrices of a single variable. This function also determines a class or collection of propositions as shown. Thus, the values of this second order matrix are still elementary propositions. Each proposition in this class of propositions is also the value of some first order matrix. Thus, the values of this second order function generate no new propositions. However, no first order matrix determines this particular collection of elementary propositions. Similarly, let G of phi exclamation mark blank be the second order matrix which has values of the form phi exclamation mark b. This function determines a class of propositions as shown. Again, no new elementary propositions are generated that are not already values of some first order matrix, but the particular class of propositions to which this second order matrix corresponds is not accounted for by any single first order matrix. So now suppose that we have the first order matrices of two individual variables as shown. Note that here we can make use of axioms 1.7 and 1.71 to combine the elementary propositions to form new elementary propositions. Also on page 134, in what follows, the single letters P and Q will represent elementary propositions, and so will phi x, psi x, etc. This quote from page 134 does not assume that x is an individual, just that phi is some function and the variable x ranges over some suitable type which may or may not be individuals. And now suppose we have the second order matrix f of phi exclamation mark blank, which has values of the form as shown. Then this second order matrix corresponds to the class of propositions of the form as shown on the screen, which of course are values of the functions phi sub k primed, etc. Thus again, no new elementary propositions are generated, just the particular collection of propositions determined by the second order matrix is not determined by any particular first order matrix. If we have the second order matrix f of phi exclamation mark blank psi exclamation mark blank, which has values of the form phi exclamation mark a implies psi exclamation mark b, then this will determine a class of propositions as shown, which can all be easily seen to be values of suitable first order matrices. Again though, the particular class of propositions is not possible through any single first order matrix. Thus we see that the values of second-order matrices are all elementary propositions that are already the values of first-order matrices. If all we're interested in is just the totality of elementary propositions, then we needn't consider second-order matrices. If, however, we want to gather propositions together in certain ways to form certain classes of propositions, then this may only be possible through the use of second-order matrices, and more will be said on this later. Indeed, the same kinds of ideas apply to higher-order matrices. Third-order matrices will still have elementary propositions as values, but the classes of propositions that they determine may not be possible through first- or second-order matrices alone. So I understand propositions of a class of propositions determined by a given matrix to be of a certain constant form. The first-order matrices correspond to the simplest forms, second-order matrices to more complex forms, third-order matrices to even more complex forms, and so on. And I might compare this to composition of functions. Suppose we have the three basic functions, f of x equals x squared, g of x equals sine x, h of x equals e to the power of x, defined on R. We have certain relations determined by each of these functions. Now suppose we compose two of these functions to give gf of x is sine x squared. This composite function determines a relation that none of the basic functions determines. It's a more complex form of relation. We can go further and form the composite function hgf of x equals e to the power of sine of x squared, which determines an even more complex form of relation which the basic functions, nor any of the pairwise composites, will determine. To form this particular relation, we have to compose at least twice. But this more complex relation ultimately only depends on the original relations that were determined by the basic functions. Thus, in a sense, no new relations have been formed. It's just the way that we collect the basic relations together in increasingly complex ways that's only made possible through this operation of composition. This process of composition produces a kind of hierarchy of functions. The higher up the hierarchy, the more complex the functions become, and hence also the relations that they determine. In a similar way to if composition of functions didn't lead to greater generality, then it wouldn't be needed and it would be quickly forgotten about. And similarly, if the higher order matrices didn't allow new ways of combining objects and greater generality, then they wouldn't be needed and would be forgotten about. And in fact, in the context of the propositional hierarchy, that's just what we're going to do. Nevertheless, in the context of the functional hierarchy, it isn't the values of matrices that we're interested in, really. It's the other functions that arise through generalization of the variables of matrices, and thus, in the context of the functional hierarchy, we need to keep the higher order matrices. So we see the values of matrices of any order are elementary propositions. But we also see that first-order matrices of the form phi, x, y, z, and so on, are sufficient to generate all elementary propositions. I make a further claim that every elementary proposition is the value of some first-order matrix of a single variable. So let's take a look at how this might be shown. Suppose we have the first-order matrix of two variables, phi, x, y, which has values, which of course are elementary propositions, of the form x is A implies y is B, where A and B are predicates. The values of this function are as shown. But now suppose we have a first-order matrix of a single variable, psi x, whose values are of the form x is A implies A is B. Then by varying x, we obtain all of the propositions in the first row. If we have another first-order matrix of a single variable, chi x, whose values are of the form x is A implies B is B, then by varying x we obtain all of the propositions in the second row. And thus it's clear that every elementary proposition obtained from the matrix phi xy can be obtained from some first-order matrix of a single variable. And of course this idea can be extended to first-order matrices of any number of variables. Their values will correspond to suitable classes of first-order matrices of a single variable. Therefore, when we want to consider the totality of elementary propositions, we can assume these to be of the form phi x. In the context of the propositional hierarchy, all other matrices become largely irrelevant. However, these other matrices still have relevance in the functional hierarchy, which I'll explain later in the video when I compare and contrast some of the properties of the two hierarchies. So now we see why on page 57 of the introduction it's stated that all elementary propositions are of the form x. Thus the elementary propositions that we need are values of functions, matrices, of the form x. So the totality of elementary propositions is the totality of values of first order matrices of a single variable. That is, the totality of variables of x, where blank ranges over first order matrices of a single variable. However, as we read on page 57, the function x is not limited to being a matrix. It's a predicative function of an individual. Indeed, when we limit the blank to matrices, then we've seen the values are elementary propositions, and in fact all elementary propositions can be obtained in this way. But as already quoted, the authors make the claim that they, elementary and first order propositions, are of one or other of the three forms as shown, where x is a predicative function of an individual. So let's have a look at how this claim can be justified in respect to first order propositions. Note if we take the interpretation of predicative function given in chapter 12, what the authors say on page 57 doesn't work as far as I can see, or at least it doesn't work as well. So you can save yourself a lot of time by making that observation, speaking from experience. It may be thought that since all elementary propositions are of the form x, then it's obvious that all first order propositions are of the form for all x phi x, or there exists x phi x, where phi x is a first order predicative function of a single variable, not several variables. But I don't think that this is at all obvious. In the following comments, the first order functions, which of course include matrices, are not restricted to functions of a single variable. On page 57, elementary and first order propositions will be values of first order functions. On page 170, first order propositions will be such as result from applying generalization to all arguments of a first order matrix. Considering the passage from page 170, how do we account for propositions such as that's shown on the screen now, where phi and psi are first order functions, indeed matrices? This is a first order proposition. Which first order matrix do we apply generalization to in order to get this proposition? The difficulty here is that we seem to have two variables, and moreover, one of the apparent variables has a limited scope. We also read on page 169, any possible function other than a matrix is derived from a matrix by means of generalization, i.e., by considering the proposition which asserts that the function in question is true with all possible values, or with some value of one of the arguments, the other argument or arguments remaining undetermined. Thus it would seem to follow that if any function can be obtained from generalization of a matrix, then any predicative function should be obtainable by generalization of a matrix, since predicative functions are, unsurprisingly, functions. It's clear that phi x, or for all y psi xy, is a function of a single variable x, and can, as we're told on page 169, be obtained by generalization from a matrix. But which matrix? There only seems to be one sensible choice of matrix, which is phi x or psi xy. But if we generalize the y variable, we obtain for all y phi x or psi xy, which doesn't agree with what we need. It may appear at first glance that a function such as phi x or for all y psi xy could not be derived from a first order matrix by generalization, but actually it can be derived from such a matrix. If we take the definitions from chapter 9, and hence use the approach given in chapter 9, then phi x or for all y psi xy is by definition 9.04 for all y phi x or psi xy, and thus is derived from the matrix chi xy whose values are of the form phi x or psi xy by generalizing the y variable. And moreover, this function is a predicative function since it is of least order compatible with its argument. Therefore, the first order proposition for all x phi x or for all y psi x y, where psi is a fixed function, is a value of the variable for all x phi exclamation mark x. Remember that when dealing with the propositional hierarchy, we're careful not to eliminate propositions based on their formal equivalence with other propositions. Just as we wanted to retain all elementary propositions so that when we generalize over elementary propositions, we are generalizing over truly all elementary propositions, we want to retain all first order propositions. So by saying that phi x or for all y psi x y is by definition for all y phi x or psi x y, I'm not potentially discarding a class of propositions based on their formal equivalence with another class of propositions. There is only one class of propositions to start with, and we're just expressing the propositions in their unabbreviated forms. The approach given in Chapter 10 doesn't seem to be as convenient to consider in regards to the propositional hierarchy, since the definition from Chapter 9, which we've used, 9.04, is effectively a demonstrable proposition in Chapter 10, Proposition 10.2. So, though what I've said really only scratches the surface, it doesn't take too much imagination to see that first order propositions of more complex forms can also be obtained in a completely analogous way. So now we can form functions of elementary propositions, fp, where p is a variable ranging over the totality of elementary propositions. So fp can be written as f of phi exclamation mark x, which is a function of a first order matrix and an individual, and thus a second order function. Moreover, if we generalize, we obtain for all p f of p, which is for all phi and x, f phi exclamation mark x. And this is by definition a second order proposition. Note that when we generalize over the variable p, this corresponds to generalizing over both phi and x simultaneously. Also note that if we have a function of a single variable ranging over elementary propositions fp, then when we form for all p fp, we do not obtain first order propositions. In fact, we obtain a second order proposition. The terminology first order proposition, second order proposition, etc. does not apply directly to the propositional hierarchy, but to the functional hierarchy. See page 58, where nth order propositions are defined in terms of apparent variables in the functional hierarchy. Different types in the functional hierarchy do not necessarily correspond to different types in the propositional hierarchy in a clear-cut way. In fact, we haven't really even got a notion of different types in the propositional hierarchy, and certain types that occur in the functional hierarchy, but which we might not need to consider when working with the functional hierarchy, may still be relevant to the propositional hierarchy. There are still different types of proposition in the propositional hierarchy, but it seems that they will have to be determined potentially in a different sense, and I'll try to give some explanation for this later in the video. So similarly, we can have a function fp where p ranges over first order propositions. This is equivalent to a function f of for all x phi exclamation mark x, and thus generalizing we obtain for all p fp, which is for all phi f of for all x phi exclamation mark x, which again is by definition a second order proposition. So second order propositions can be obtained by generalizing the variable of a function of elementary propositions, or by generalizing the variable of a function of first order propositions. Now of course, we can have functions of several variables ranging over elementary propositions or first order propositions, and also higher order propositions can be derived by continuing this process. Now a lot of what follows in the rest of this video is guesswork and may not be correct. So I suppose if we have a function of two variables, f of pq, where each ranges over elementary propositions, then this is a function of the form f phi exclamation mark x psi exclamation mark y. That is a function of the variables phi exclamation mark blank, psi exclamation mark blank, which both range over first order predicative functions, or first order matrices, and x and y, which range over individuals. Thus generalizing, we obtain for all p and q, f of p and q is of the form phi psi xy, f of phi exclamation mark x psi exclamation mark y, and is thus again a second order proposition. Similarly, if f of pq is a function of two variables, p ranges over elementary propositions and q ranges over first order propositions, then we have a function of the form as shown on the screen. That is a function of the variables phi exclamation mark blank psi exclamation mark blank ranging over predicative first order functions, and x which ranges over individuals. And thus, for all pq, fpq will be of the form as shown, which is, of course, a second order proposition by virtue of the fact that there is an apparent variable of the first order from the functional hierarchy, and so on. We read on page 57 to 58, a proposition involving the totality of first order propositions may be reduced to one involving the totality of first order functions, and this obviously applies equally to higher orders. So second order propositions are obtained from second order matrices, a matrix being a type of function from the functional hierarchy. Suppose we have a second order matrix as shown, then we obtain a second order proposition by generalizing all of the variables. Now, as we've seen, if we have f of p, where p ranges over elementary propositions, and g of q, where q ranges over first order propositions, then for all p, f of p, and for all q, g of q, are second order propositions. Are they the same type or different types? I actually don't know for certain. If we look at the corresponding expressions in terms of the functional hierarchy, then it would seem that they are of different types. However, what counts as a well-defined type in the functional hierarchy doesn't necessarily count as a well-defined type in the propositional hierarchy. In the functional hierarchy, there is more focus on form rather than content. Thus, we see that elementary propositions, which can all be considered as being of the form phi x, can also be considered as being of other forms, say phi xy or phi xyz, etc. Thus, data which appears to be the same as regards content can be considered as having different forms depending on how the data are analysed. Different forms correspond to different types, even if the content is the same. We can discard whole swathes of propositions, but the propositions that remain can be analysed in a multiplicity of ways. The proposition A is A implies B is B can be thought of as a value of the one variable function x is A implies B is B, or a value of the two variable function x is A implies Y is B. On the other hand, with the propositional hierarchy, content is more important than form, it seems. We've seen how functions of different forms can account for the same content. So in effect, we can disregard the different forms and focus more on the content. Thus, whether for all p f of p and for all q g of q determine the same or different types depends potentially on how we view things. So in the functional hierarchy, there's a focus on form at the expense of content. In the propositional hierarchy, there's a focus on content and a relative disregard of form, and I'll say a bit more about this later in the video. But on this basis, we might consider all propositions of a particular order as just all being of the same type, irrespective of which function or functions from the functional hierarchy a given proposition might correspond to. If we take second order propositions as an example, all second order functions do is carve up the totality of second order propositions in certain ways on the basis of form, and we call these, in the functional hierarchy, types. However, they're still all second order propositions. And since we're not concerned with form but content in the propositional hierarchy, then there seems to be no good reason to have different types of second order proposition in the propositional hierarchy. We might also incline towards the opinion that all elementary propositions and first order propositions as forming together a single type in the propositional hierarchy. We see on page 134, from the purely technical point of view, the distinction between elementary and other propositions may be ignored, so long as propositions do not appear as apparent variables. This may suggest that elementary propositions and first-order propositions together could be considered as forming a single type. Now, I quoted this earlier in the video from pages 57 to 58, a proposition involving the totality of first-order propositions may be reduced to one involving the totality of first-order functions. Notice that the authors speak of the totality of first-order propositions. Is this to be understood as meaning that all first-order propositions are to be considered as being of the same type? However, notice also that the authors speak of the totality of first-order functions. Yet first-order functions are split into types in the functional hierarchy. This seems to suggest that we can speak of a totality of objects of different types. Thus we seem to be free to choose whether and how we split a totality up into types. There may be different ways that a single totality can be split into different types. No one way is the correct way. There are just different ways. And what we want to do may ultimately determine how we split things up. If on the one hand we accept each order of proposition as forming a single type, then the question for me becomes, just as we saw for elementary propositions and first-order propositions, they can be generated by a relatively small number of functions. Can we find a correspondingly small number, or even a minimal number of functions, for each of the other orders of proposition? To this, I currently have no answer. If we take this view, then it would seem to me that the propositional hierarchy is not going to be rich enough for us to deduce the type of mathematics that we want. This simple version of a propositional hierarchy seems to be potentially too simple. On page 58 we read, "The propositional hierarchy is never required in practice and is only relevant for the solution to paradoxes. Hence it's unnecessary to go into further detail as to the types of propositions." And on page 29 of the introduction to the second edition we read, "Every elementary proposition is a value of phi exclamation mark blank. Therefore, for all p, f of p is equivalent to, for all phi and x, f of phi exclamation mark x, and there exists p such that f of p is equivalent to, there exists phi and x such that f of phi exclamation mark x. Hence, all second-order propositions in which the variable is an elementary proposition can be derived from elementary matrices. The question of other second-order propositions will be dealt with in the next section. So the authors here seem to suggest that there are different types of propositions. But if we want to split the orders of propositions up into different types, how will we do this? On what basis are we to distinguish one type of proposition from another? And ideally, without reference to the functional hierarchy. Again, to this question, I have no definite answer right now. With the functional hierarchy, we're interested in forming classes of individuals, classes of individuals, and so on. We're not interested in forming classes of propositions. We're able to discard certain propositions and still be able to form all of the classes that we need and want to form. We don't need all of the propositions. Indeed, if two functions in the functional hierarchy are formally equivalent, that is, they correspond to different classes of propositions, but for each argument, when the proposition from one function holds with that argument, so does the proposition from the other function and vice versa, then in that case we can effectively discard one of those classes of propositions because the two functions determine the same class of terms. When we generalize in the functional hierarchy, we generalize over individuals or functions of individuals. And generalizing over functions can be thought of as kind of generalizing over classes of individuals. It isn't exactly the same, but there is a close link between the two ideas. So as long as we have sufficiently many functions, then we have all of the classes accounted for that we need. So when we generalize, we're generalizing across all classes. Of course, there may still be some formally equivalent pairs of functions remaining, and hence some duplication of classes, but we don't insist that there be a one-to-one correspondence between functions and classes. In the functional hierarchy, we can cut out whole classes of propositions that effectively serve no purpose for us. We could keep them in if we wanted, but it would create a system that's unnecessarily complicated, and the added complexity would not add anything useful. Hence the reason why we often ignore, although not completely, second-order functions of an individual variable, or third-order functions of an individual variable, and so on. Or more generally, we largely ignore non-predicative functions in many contexts. Of course, using the notion of predicative function from chapter 12, we're able to disregard many more forms of function. However, When it comes to the propositional hierarchy, now we want to generalize over propositions. We need to make sure that we have all of the propositions, because now it would seem that we're forming classes from propositions rather than classes of individuals and functions and so on. So in this case, we have different ideas about what we keep and what we discard. If the values of a function determine the same propositions as another function or class of functions, then we have some redundancy in the system, and depending on the circumstances, we may discard the single function and keep the class of functions, or keep the class of functions and discard the single function. Just like when we discarded all matrices other than first order matrices of one variable earlier in the video. What we want to be sure of is that when we generalize over propositions, we're generalizing truly over all propositions. It also seems that the axiom of reducibility as formulated in chapter 12 is suitable for the purposes of the functional hierarchy, but not necessarily suitable for the propositional hierarchy, since the axiom of reducibility gives a way of eliminating classes of functions which are inconvenient, and though they determine their own classes of propositions, determine the same classes of individuals or of functions and so on, as certain other functions do. There may be a need for an axiom of reducibility formulated for the needs of the propositional hierarchy. Certain functions of propositions may be redundant in some way, and this is suggested on page 194, where the authors allude to the propositional hierarchy with a reducibility axiom, such as 12.1. The axiom of reducibility for the functional hierarchy appears to be inappropriate in many ways, since it effectively eliminates classes of propositions on the basis of their redundant content. An axiom of reducibility for the propositional hierarchy would presumably be required to eliminate propositions on the basis of redundant forms. I haven't thought about this enough, and to be honest, I probably won't get round to thinking about this in much detail, at least for the foreseeable future. So I think that what I've said so far gives some idea about how, at least in theory, the propositional hierarchy might be derived from the functional hierarchy. The authors themselves don't really say much about the structure of the propositional hierarchy. What we might like to try to do is to form the propositional hierarchy independently and without reference to the functional hierarchy. As it stands, the propositional hierarchy is seen largely through the lens of the functional hierarchy, but we'd like to try to make them more independent, if at all possible. I haven't gone through this in detail, but I suggest that the development of the propositional hierarchy from scratch and independently of the functional hierarchy will follow a similar line of reasoning as I gave in my video covering the construction of the functional hierarchy. I do think that the different order propositions will need to be split up into different types, and I think that there will be analogues in the propositional hierarchy corresponding to concepts such as matrix, predicative function, type, axiom of reducibility, and so on. My expectation is that we will have matrices in the functional hierarchy whose variables range over types of proposition, and propositions will be obtained by generalizing the variables of these matrices in any order. Propositions derived from these new matrices with the same variable combination will possibly determine propositions of the same type. Now, there is one point that I'm undecided on, which is whether to have on the lowest level as just a single class of propositions consisting of elementary and first order propositions together, or whether to have two different classes, one consisting of elementary propositions and the other first order propositions. Now, bear in mind that if f of p is a function with variable ranging over elementary propositions, we do not obtain a first order proposition from generalization, but a second order proposition. Maybe we could even get by with just elementary propositions, or just first order propositions. Maybe let me know what your ideas are on this. I won't go into any more detail in this video on the construction of the propositional hierarchy. I think I've said all I can say about its construction based on what little information is available to us about it. Why would we use the functional hierarchy instead of the propositional hierarchy? Well, by using phi x, psi x, etc., we potentially get a finer division of propositions. We can split propositions into classes of propositions which have a constancy of form. For example, in Principles of Mathematics, in section 82, we read, "It would seem to follow that propositions may have a constancy of form, expressed in the fact that they are instances of a given propositional function." It's worth bearing in mind that at the time of writing Principia Mathematica, that simply considering propositions as truth values was not a done thing, at least not in the first edition. It's also clear from certain parts of Principles of Mathematics, such as Chapter 4, that propositions are considered by Russell to have constituents. That is, that propositions can be analysed, for example, into a term and something about the term. The individuals of Principia Mathematica seem to correspond to the terms of Principles of Mathematics. So on page 168 we see propositions which contain no apparent variables we call elementary propositions, and the terms of such propositions other than functions we call individuals. Then individuals form the first type. And we also read on page 169, we may explain an individual as something which exists on its own account. In applying the process of generalization to individuals, we run no risk of incurring reflexive fallacies. On pages 53 to 54, such objects, individuals, will be constituents of propositions or functions, and will be genuine in the sense that they do not disappear on analysis, as for example classes do. Additionally, on page 46, Russell considers propositions to be incomplete symbols, but individuals as being actual objects. Propositions are described as incomplete symbols. Whitehead and Russell explain this as follows. The proposition Socrates is human uses Socrates is human in a way which requires a supplement of some kind before it acquires a complete meaning. But when I judge Socrates is human, the meaning is completed by the act of judging, and we no longer have an incomplete symbol. Moreover, a proposition, according to Whitehead and Russell, is not a single entity. On page 51 we see, a proposition is not a single entity, but a relation of several. Hence a statement in which a proposition appears as the subject will only be significant if it can be reduced to a statement about the terms which appear in the proposition. There are also certain issues with certain propositions where the grammatical subject of the proposition may not denote any object at all. So considering Russell's views on propositions, it seems very natural that he would opt for the functional hierarchy on which to base his development of Principia Mathematica. So thankfully that just about wraps things up for this video. This has been an incredibly difficult video for me to make. I've had to rewrite the contents of this video several times. I'd write out what I wanted to include and then I'd figure something else out that I wanted to include or that needed to replace something else. It's been a lot of work. When it comes to making these videos, my only hope is that there is something useful or interesting in this video for someone somewhere. I'm an amateur and I'm not involved in research or academia, so I do this purely as a hobby. So please don't take what I say in this video or any of my videos as scholarly research. It's not. If there's anything useful for you in this video, then please feel free to take what I say and develop the ideas more thoroughly. Of course, if you have any questions, then please feel free to ask, and I'll be happy to help however I can. Furthermore, if you have anything to correct me on, or that you would like to add, then please let me know. Thank you for watching. Don't forget to subscribe and give this video a like. Please share this video with anyone that you think may benefit from it, and with that I will say ta-ta for now.